We can go on to 4.2, solving a 2x2 system of linear equations by, this is a new method, substitution, which we kind of did discuss just a little bit and very briefly there in 4.1. So remember this problem that we did in 4.1, right? Now, I'm going back specifically to the system. Remember that it says y equals -5? That means that you can just automatically pretty much really replace this y here with -5, and then you're just looking at principles of equality to solve this. That's what we mean by substitution, because I just took this y value, which I knew it was, it's just a number, and I replaced it with a value that I knew it was. Now, is it always going to be this pretty, where it's just -5? No. Sometimes it may be like -5x plus 3. All right, then it's -5x plus 3 instead. See what I'm saying? I know that's kind of sloppy right there, but we're going to be looking at methods, this method, which is just substitution. You replace whatever letter you have with whatever number or expression that you have as well. So here's a nice, I guess, process for solving systems with substitution. So, and it may be necessary to manipulate an equation so that you just have one variable on its own side of the equal sign. And really what you'd like to do, at least when we're starting out, is to replace or to make the letter you're solving for just have a coefficient of 1, okay? Just like we've been seeing. Pretty much like changing standard form into slope-intercept form, pretty much. Now, if you change it into slope-intercept form, you're pretty much committing yourself to always replacing the y values, which if that works for you, so you don't have to remember so much or think about it so much, then that would be fine, okay? But you may see sometimes where it's going to be very fast to replace the x value because one of the equations just may be x equals 2y minus 3, something like that. Okay, then replace the x because it's faster, all right? Now determine what one of the variables equals as an expression. Yep, that's like making the coefficient of 1. Replace that variable in the other expression. Then we treat that as a one variable equation that we solve for the variable. And then once you get that value, this is crucial. This is where you come up with the second value, where now that you know that number, you replace that number into that variable, and then you solve for the second one. And it doesn't really matter which of the equations you use. Yeah, just make sure you check your answer at the end. That's pretty crucial, which we saw in the last section. And we want to make sure that our final answers are going to be true, okay? But none of this will require any graphing. And so most of the answers I would think are going to come out as some kind of fractional values. Whether they do or not, I don't know. Now, another thing we saw on the last section was that it's possible for the graphs to never intersect if they're parallel. We may see some of that in this section too, or we may see infinite solutions. We'll see. 3x plus 2y equals 41, and then that's our first equation there, and then the second one is 2y equals 8. Now, just while we're getting used to this, I'm going to do this twice, by the way, just so you can see. Again, if you're thinking outside the box, you'd notice something right off the bat in this one, okay? Especially when it comes to substitution. I'm gonna ignore that, and then I'll get to it, okay? So right off the bat here, I can see, and it may take some analysis of these two equations to see which one is easier to solve for. I can see that this second equation is just 2y equals 8. There's no x's, there's no addition or subtraction, it's just 2y equals 8. So I know I can solve for y pretty quickly by dividing both sides by 2. And then I can see that the y value, 8 divided by 2, is going to be 4. Now that, by the way, is y equals 4, which means that in my ordered pair, my final solution, hey, the y value is going to be 4. Okay, I just need the x value, okay? Now, since this method is substitution, let's look at the second equation. So I'll just copy this here. 3x plus 2y equals 41. But now we know the y value is 4. Now, again, this one's nice because it came out as an actual whole value, but that won't always happen, okay? So you could get like y equals 3x plus 1, and in that case, you would replace it here. But we already know the value is 4. So I replace that y value with 4, and then I proceed to solve for x. So, principles of equality, but first some simplification. 2 times 4, that could be even considered distribution, but now I got 3x plus 8 equals 41. Then I would personally subtract 8 from both sides. So 41 minus 8, 733, which now equals, that zeroes out, and I'll drop my 3x. So 3x now equals 33. We'll divide both sides by 3, and that's an x value right there of 11. So as of right now, that should be my x value. And once again, we can check for truthfulness though. Of course, if you go in there and you replace the y with 4, that's gonna make this one true. But let's check this other one. So if I replace the y with 4, which we've done already, but now I'm gonna replace the x with 11. Is this one gonna be true? So that'd be 33 plus 8. Yeah, that's gonna be 41, so that's true as well. All right, that again means that if we went to the graph on this, which we're not gonna do as much as you may want to, if we went to the graph on this, this would be the ordered pair where the two lines intersect, okay? Now, let's talk about that, kind of the second method. If you can just notice some things on this, right? And yeah, it's true that we're kind of focusing on this 2y business right here and here. Now, of course, you could solve this one very quickly for y, and that's fine. But what this means is that if you take that equation, 3x plus 2y equals 41, and you replace it with this this 2y, which now is 8, you could do that. So instead of it showing as 2y, I could just, if I wanted to, replace it with 8. Okay, now does this happen all the time? No, it doesn't. But it does mean that if you wanted to manipulate things to match each other, you can. All right? And of course, you'd solve this and you'd find x is 11, and then you'd come back to this one. You could replace the x here and then solve again, but this one's clearly very easy to solve for y. And yeah, we already checked our answer. 11.4 is the solution to this system. But on this problem now, we got an x equals an expression, negative 1/4 y, right? Now that is a direct equals right there. That tells me directly what x is. So that means that where we're kind of used to replacing y's, at least from that last problem anyways, on this problem, I get to replace the x. So I'm going to go to the first equation, negative 8x plus y equals 2. And that, by the way, was kind of the analysis to see which one is going to be easier, not just to replace, but to solve for. And this one's already solved for us. It solves for x. So I'm going to go into my equation there, and I'm going to replace x with this value, this expression that it gives us, negative 1/4 y, right? I should have given myself more space. Negative 1/4 y. Sorry, that works. All right, then I solve this. Okay, so it's a negative 8 times negative 1/4 y is going to be 2y. And then, of course, we still got the plus y equals 2. And then, we'll combine our y's there. That's a 1y. That's going to be 3y's equals 2. Here's a fraction, right? Good fraction right there. Divide both sides by 3. And I get y equals 2/3. I ran out of space below. Sorry about that. But yeah, that's going to be our y value. All right, so that's my y value, and I can go directly to the ordered pair right now and just plug that in for my y value at 2/3. Okay? Now that we have a y value, again, you could use either one of the equations to solve for its corresponding x value, but I see that for this second equation here, it's a direct calculation for x, meaning all the operations are on y, and then it solves for x. It equals x. So I'm gonna use that equation, x equals negative 1/4 y, but now I replace the y with the value that we found at 2/3. And then we just solve this. I'd use cross simplification right there, and then I get, I'll use a different color. X equals negative 1/6, looks like, negative 1/6. Okay, now I'm going to use my calculator to check this because I got some fractional values there which don't look very pretty. I don't really need to check the second equation, although you could, right? Negative 1/4. Oh, dang it. Come on, calculator. Negative 1/4 times, I guess, 2/3 there. So yeah, it's negative 1/6. The second one is proved true. Then the first one, negative 8 times the x, which is negative 1/6, parentheses, plus y, which is 2/3. enter, it is 2, yeah, so that's true as well. Both equations ended up being true when I replaced the x and y values with their, with the values we found there. All right then, if you guys are feeling pretty good, try this one out. See if you can solve this one using substitution, and then we'll go over it. So, again, not too much analysis on this one because the second equation is y equals something, right? If I can go to my first equation and replace that y with that, whatever that something is. So that's 2x plus y, and that's the first equation, equals, and give myself enough room, hopefully. This y, I'm going to replace with this part of the expression of y, because that tells us what y is, which is, some people even prefer to see this with parentheses right here, okay? And if you like to do that, that's fine. If this is plus, we don't really need it. If it was minus, then we would, okay? Keep that in mind, because if it's minus, then we'd have to change the signs of both parts. Some people just do that right off the bat too. That's fine. Okay, so I know I don't really need to distribute a 1 because that's the identity property for multiplication. And so right here I'm looking to combine my like terms. That's 4x's minus 2 equals 8. And then, you know, principles of equality here. So there we go. Let's add 2 to both sides. Kind of to sandwich that in there. So 4x equals 8 plus 2, which is 10. Divide both sides by 4. And just simplified, I got 5 halves on that. Like this. Okay, so that should be my x value. And, you know, if you wanted to put that into the ordered pair, that's fine. I'm gonna wait though, okay? So now that I have that x value, again, we have 2 options here. We can either put the x value into this equation and solve for y, or we can put it into this equation and solve for y. You can do both if you wanted to. I'm gonna use the second one, and there's a reason for that, okay? So I got y equals 2x minus 2. So we solve for x here in purple. This equation here, that I've now written here, if I replace this x, all the calculations are with x, so that it'll give me the y value that corresponds with it straight away. So I'm going to go in there and replace the x with 5 halves.
And you get 5.
So solving this, yeah, 2 times 5 halves is 5, and then I'd subtract the 2 right there, and then that'd be 3. So it looks like the final y value here is 3. And so my ordered pair, set this up, 5 halves 3. But let's go and check. So let's kind of get it in there. So I know the x value should be 5 halves. So let's go and replace the x with 5 halves. And then the y value of 3. And yeah, since you guys were doing that, I kind of checked already. This does equal 8, so that's true. And then even the second one, I already replaced that, the x value with 5 halves. And the y value 3, which we kind of did just in the regular solution, but when I checked that, I found it was true as well. So now I know that this is the actual solution to this system of equations. So on this one, we'll do this one together. And again, this one, both these are, I guess they're not in standard form, but they're not a direct y equals or x equals on this one. Now, we can quickly make this top one an x equals. You could, with 2 principles of equality, you could change this into x equals as well. It doesn't really matter which one you choose. I'm going to go with the easier of the 2 options and take my 2x equals 6y minus 16 and solve for x, because then I would just need to divide all the terms by 2. So that gives me x equals 3y minus 8 right here, okay? Well, now I do have an x value, x equals 3y minus 8. So I'm going to go to the second equation. Negative x plus 3y equals 8. And I'm going to replace the x with the expression we just found for x. And yeah, it's negative, so I will need some parentheses there, by the way. 3y minus 8. Now just solving for an old-fashioned equation right here at this point, I'd say maybe even distribute 1. Some of you just change the signs, that's fine. Negative 3y plus 8, that works. And then plus 3y equals 8. And this goes back to our first module, because when I combine my y's here, I get 0 y's. You can say you're going to drop your 8 equals 8. And then even to go take this just a little bit further, you subtract 8 from both sides, you get 0y equals 0, okay? Now, at this point, we don't really need to go any further because I know right now that anything times 0 is 0. So this one, I like to just say that it's always true. In the past, we've seen that as infinite solutions, which is the case, right? And that actually finishes this one out. Infinite solutions. Oh, I do better than that one. All right, infinite solutions. You mean we didn't really have to solve for x? Not at this point, because once we found that the y's were always going to be true, that means that the x values will always be true as well. At least when they fall on the lines, right? Of course, we'd never ask you to find all the ordered pairs that would make it true, because there's so many. But if we go back to what we saw in 4.1, that means that if you were to graph these two lines, it's the same line both times. To me, I look at this one as half the work, so I like it, you know. It may be kind of weird right now to see that, and it's like, we can just finish right here, especially when you get enough experience. Like, shouldn't we be doing a little bit more? No, because we found that's true. All right, this one's a direct x equals. That's okay. Let's go ahead and see what this one gives us. I'll make this a little bigger. Yeah, if we get fractions, we'll make that our answer. But right here it says x equals 10 minus y. So I go to the other equation, 2x plus y equals 18, and I replace the x with that expression. Okay. Now, this one, the x was being multiplied by 2, so I need to multiply 2 by the full expression of 10 minus y. Okay, so I'm going to solve now for y, just like we would a regular equation, by distributing 2. 2 times 10 is 20. 2 times negative y is negative 2y plus y equals 18. Not really color coordinating this very well, but combining like terms, negative 1y, so 20 minus 1y equals 18. Subtract 20 from both sides. And then we'll drop the negative 1y, which equals negative 2 now, but dividing both sides by negative 1 makes the y value a positive 2. So now we have a y value, but we go back to both equations. Again, it doesn't matter which one you choose to replace y with. It should be a true statement for both. So I'm going to choose the second one because, again, all the operations are with the y. So when I go into that one and replace the y with the value we just found, which is 2, then it will solve directly for the x, which won't always happen, but you know, sometimes we get lucky like that. So 10 minus 2 is 8. Boom, x equals 8, which means our ordered pair here would be 8, 2. No fractions on this one, kind of surprising, but it happens. I think that's pretty good. Let's just check, right? So I'm going to go up here, replace the x with 8. And then the y value with 2, let's check for truthfulness. That'd be 16 plus 2, which is 18, that's true. And then the second equation should be 8 equals 10 minus 2. Yeah, we've already verified that, so that's true as well. Since they're both true, now I know for sure that this is the solution to this system. Well, for this system, it's going to be pretty much the same as one of those last ones, so we gotta analyze these first, right? So I see y equals 4x plus 6, which means I can plug in a y value easily with this expression right here. So I'm going to look at this top equation and then replace the y value with this expression right here. So there's that top equation, and now I'm going to replace this y with the expression from what y equals, 4x plus 6. And then this sets up an equation that I can then solve. So I'm distributing first. That's a negative 6, by the way, because of the minus sign out there in the front. So that's negative 6 times 4x first, which would be negative 24x's. And then negative 6 times positive 6 would be negative 36. Nothing else changed. So this is what I have now. And now that I've done some distribution, I'm looking for any like terms to combine. I see 2x's minus 24x's, which would result in negative 22x's. Everything else stays. And then some principles of equality here now to finish solving this equation. So I see I got the negative 36 with the x's right there. So I would want to zero out this negative 36 by adding 36 to both sides. So plus 36 there. And then I'll drop my negative 22x's. And then the negative 36 zeroed out, just like we had planned on. And then I just put this in my calculator, negative 58 plus 36, and I get a negative 22 right there. So I got negative 22x's equals negative 22. From here, all we got to do is divide both sides by the coefficient, which is negative 22. That becomes a phantom 1x, which now equals negative 22 divided by negative 22 is 1 as well. Okay, so I see that my x value is 1, and so I can go now to my ordered pair, and I know now that the x value is 1. I'll check in the end just to make sure. But now that I know my x value is 1, I'm going to look through both equations, see if there's one that's easier to solve for y. And yes, this one is, because I'll multiply by x and then add, then I'll have the y directly. So I'm going to use y equals 4x plus 6. And then I'm going to go in and replace the x value with the x value we just found there in blue, which is 1. Okay, so I'm just solving for the corresponding y value. So 4 times 1 is 4, then plus 6, that's 10. And I get y equals 10. So my y value is 10, my x value is 1. Then we can go back and check, right? So 4 times 1 plus 6 is 10. That checks off. But I can go up here and replace in the first equation x with 1 and then y with 10 to see what happens. And when I put this in my calculator, I got negative 58, so that shows that it would be true. And since it's true, then I know for sure that 110 is the actual solution to this system of equations. So here we got one with fractions, and both are in slope-intercept form, by the way. So it kind of goes back to that first example we saw where it was y equals negative 5, then we replace the y with negative 5. It's just now y is an expression, so I'm going to replace either one of the y's. It doesn't really matter because I know y equals this, but y equals this as well. We got to see where they're the same, and that's going to be the first y. I'll do this one in red. It's negative 9/4 x plus 86. Equals the second one, which is negative 8/3 x plus 101. Okay, what I did right here is I took the first equation and I replaced what y was, negative 9/4 x plus 86, and I replaced this y with that. That's what I did right there, okay? And now I have an equation with just one variable, and so I can now proceed to solve this for that one variable. And so I like to use just straight principles of equality. I did see on the previous exam that some of you prefer to get rid of the fractions, which is fine. Just be careful when you do it because we tend to miss some of the terms when we do that, okay? So I'm going to put my x's on the left and then the numbers on the right. So the plus 86 needs to zero out. So minus 86 here, which will zero that out. I'll drop my negative 9/4 x, which equals, I'll drop my negative 8/3 x. Maybe I should have done this one in one step. That's going to be a positive 5, 9, 15. And then, yeah, I've got to zero out the 8/3 by adding 8/3 x's. Now that's going to zero out, but I'm going to let the calculator do the heavy lifting on the x's. So negative 9/4 of my x's plus 8/3 of the x's is 5/12. So we are going to need that, and then I'll drop my 15. All right, well, let's give ourselves some space because we've got to divide both sides by the coefficient of 5/12. But again, I'm going to let the calculator do this work for me. I know that's a phantom 1, that's fine. But 15 divided by 5/12. Enter, 36. Now you can think about this as well. Like, yeah, it'd be difficult to graph fractions on a graph, put fractional values on a graph. Big numbers as well, okay, because then you'd have to expand the scale. All right, so I have an x value, but I also need a y value. Just be careful because almost inevitably there's at least 5 exams where there's a question like this, and students do all this work, they get to x, and it's the correct x, but then they stop. It's like, I solved for x, just like we did in Module 1. It's like, now we're done, right? And they may even check up here, and it's true. It's just, remember, you got to solve for the y value that corresponds with it. It's an ordered pair that we need on this, okay? So let's go back to, again, it doesn't matter which of the two equations. I'll choose the top one. Y equals, I chose that one arbitrarily. I don't think it's going to make it easier for calculation. It doesn't really matter. And so I'm gonna replace the x with the x value we found at 36. And so let's go ahead and calculate here. Negative 9/4 times 36 should be negative 81. And then plus the 86 there, gonna be 5. So this is our corresponding y value. So in the ordered pair, we already found our x value at 36, and then I just found the corresponding y value. Assuming I did that right, that's 5. Now, of course, you can check, and so I'll just go to my calculator to check this stuff. By the way, I already checked the top one by replacing the x and then found its corresponding y value. I really only need to check the second one, so negative 8/3 times 36 plus 101, enter, boom, 5. And that's our corresponding y value, so that's true. Now I know that this is the actual solution. All right, so y equals 3x minus 11, and then 12x minus 4y equals negative 46. Yeah, we got a y value there at the top, so I'm going to go to the second equation and replace that y with that expression that it gave us, right? So it's a 12x minus 4y equals negative 46. Hopefully that's enough space, because the y value I will replace with this 3x minus 11 right there. So that's the y that I'm replacing. 3x minus 11, just old-fashioned equation solving strategies here. Let's distribute the negative 4 there, so that's negative 4 times 3x, which is negative 12x's. And then negative 4 times negative 11 is negative 44. Let's see what the rest of this looks like. 12x minus 12x equals negative 46 right here. And now when I combine my x's, the like terms there, I end up with 0 x's. I'm going to keep that because, well, I guess I don't have to, but I'm going to keep it just so we can continue with the problem, all right? Now, if you don't show it, it'd be fine, by the way. And at this point, you could see what the answer is. You could say, well, negative 44 is not actually equal to negative 46, and it never will be. So some people say, look, we got no solutions right here. And that's fine if you notice that, okay? If you don't notice that, then you will need the 0x. Okay, and I don't really care when you notice it. Just we need you to notice it at some point, because at this point we're going to have to add 44 to both sides. So that's going to be negative 2. I'll drop my 0x. Equals negative 2, and then, yeah, what can I multiply by 0 to get negative 2? Nothing. I can never get anything out of that that I could multiply by 0 to get negative 2. So again, we see, even at this stage, no solutions. So again, to me, that's half the work, which makes that nice, very convenient, but it's done. All right, so finally we see an equation, two equations that are both in standard form, okay? And so, again, we can look at this and say, is there one that's going to be easier to solve than the other? I would say no, not necessarily on this one, unless you noticed that the top equation, you could divide all the terms by 4, simplify it, and then you'd have at least an x by itself. But I'm going to assume that not everyone noticed that, okay? So we're just going to flow with this. We're going to say, look, solve either one of the equations for either one of the variables. It's not going to matter. And the reason why we're doing this right now is because we're going to see that it becomes kind of tedious, not necessarily monotonous, because all of math is, but this is going to be kind of painful right now. That's because there's another strategy to use when you get two equations in standard form like this, but we won't see that till next time, okay? So I'm going to take the top equation first, and, you know, I guess since we're kind of used to solving for y's, that's what I'll do. So I am choosing arbitrarily and unilaterally to solve for y. What that'll do is it'll change it into slope-intercept form, okay? And since we already have some experience doing that, that's what I'm going to do. So first thing here is to subtract 4 x's. I can't emphasize this enough. If you wanted to solve for the x's, you could, okay? I'm just solving for the y's because it's something that we're kind of used to. So I'll drop my negative 8y equals, again, I'll switch these two terms, negative 4x minus 64, and then divide all the terms by negative 8. And that gives me y equals, that'll be positive 1/2 x plus 8 right there. Now we do have the 1/2 x. No, that'll be fine in the other equation. So let's look at what that will look like now if I replace this y expression into this other equation. So that's a 3x plus 4y. Again, I can give myself some space there with the y, but that equals 46. So now I replace the y with the expression we just found at positive 1/2 x, but plus 8 right there, barely fit it. All right, let's solve this one. For x, so 4 times 1/2 would be 2x's. 4 times 8 is positive 32. And then I got 3x, that's a positive 2x, equals 46. I got some like terms to combine, that's very nice. 3x's plus 2x's is 5x's. Now plus 32 equals 46. And subtract 32 from both sides. Zeros that out. Drop your 5x equals 14. Divide both sides by 5. And that gives us an x value of 14/5. Big, kind of ran out of space there, but that works. X equals 14/5. Now, I could go back here to this equation and solve for y. I could actually go back here, replace the x with that number, and solve for y as well. But remember, we manipulated that equation right here to solve for y directly. So that's what I'm going to do. You don't have to do that. You can go to either one of the originals, but I'm going to take kind of a shortcut right here to solve for y. That's 14/5. Replace with x. And so what do we get out of this? 14/10 plus 8. So that'd be 80/10. I'm doing this by hand, but that's going to be 94/10, which will simplify into 47/5. And that would be our corresponding y value right there. All right, fair enough. Let's go and see what our ordered pair looks like then. So here's my ordered pair. I got an x value of 14/5. And then a corresponding y value, 47/5. So both in fifths. And that seems to work, but again, I'm gonna go back to the calculator and check by replacing the x and y's here in my calculator. In that first equation, when I replace the x with 14/5 and the y with 47/5, I do get negative 64 on my calculator. But I'm gonna do it with the second equation as well. Replace x with 14/5 and plus 4 times 47/5. Enter, and I get 46, boom. So that is true for both. It is true for both equations. So now I know I can box that in with lots of confidence. So we see that even though both equations were in standard form, we're going to see a new strategy when they're in standard form like this next time. But we also see that it's possible, if you prefer to use substitution, you could do that.